design procedure. So to design, first of all, we need to know about the applied loads that we can get from the analysis. So once we have the applied loads, dead load, live load and wind load, and we also have the dimension of the member, then the next step is to calculate the factored value. So if we are using LRFD design method, so then we need to convert them into factored load. Once we have the factored load, then the next step is to calculate the required area. Or we need to select the, for example, for tension yielding, we have Tn is equal to phi Fy Ag, and we know the design equation, Tu should be less than phi Tn. Applied load should be less than design capacity. So we know the applied load Tu, and this phi Tn is equal to phi Fy Ag. So if we rearrange this equation for this Ag, so we will get Ag is equal to Tu over phi Fy. So by using this equation, we can estimate the gross area which is required for the member to resist the applied load. So here Tu is the factored load, so which we already know. Fy is the yield strength of the steel. If it is a 36 steel, then it will be 250. So this is the case for tension yielding, and if we are considering the case of tension rupture, so in that case the equation will become like this. So in case of tension rupture, our equation is Tu should be less than phi Tn. So Tu should be less than equal to phi, which is 0.75, and Tn is equal to Fu times Ae, or we can write it phi Fu time, instead of Ae we can write U and net area. And if I write this net area, or if I say that the ratio of net area and the gross area is equal to R, so A net over Ag, so then I can write that this net area is equal to R times Ag. So here I will replace this An with the R times Ag. It should be greater than Tu, or Tu should be less than this one or equal to this one. So if we equate this to equation and rearrange, then Ag will become Tu over phi Fu U and R. So here U is reduction factor or shear lag factor, and R is the ratio of net area over gross area. So we can estimate the gross area required to resist the tension rupture or to avoid the tension rupture failure. So from these two equations, we can estimate the gross area for the required section. So here we have these two equations, this one and this one. So here we will input this Tu in kilonewton, then we need to multiply it with 1000, and phi is 0.9 in case of tension yielding, and in case of tension rupture it is 0.75. And U and R, U is the shear lag factor and R is the ratio of An over Ag. So initially we don't have the detail of the connection, so we can assume any reasonable value for U. So for example, we can assume its value 0.85. So normally this value is good, it is not too high and not too less, so we can assume this value. Similarly for R, we can assume the value again 0.85, mean the ratio of net area to gross area is 0.85. So it is the assumption at the initial stage. So at the later stage we can check the actual value of U and R when we have selected the connection and we have decided the connection details. So this step is to estimate or to calculate the required area. So once we have required area based on the applied load and the material strength, then we also need to find the minimum width of our minimum connected leg width. So we have already seen we can approximate this value by L over 40 if the member is 2 to 3 meter, or we can calculate this by 3.25 diameter of bolt plus 18, or we can estimate by 2.5 times diameter of bolt plus 16. This is when only one leg is connected, and this is when both the legs have bolts. Okay, so initially if we don't know the diameter of bolts, so we can assume that the diameter of rivet or bolt is 15 millimeter. So initially we can assume its value 15 millimeter. Okay, now we have the required area, minimum width. So we need to select the trial section. So the trial section will be selected based on the 4 criteria. The first criteria is selected area should be greater than required area. So the section that we will select, it should have larger area than that of required area that we have calculated based on the previous two equations. And the section should be of minimum weight. So we can find many sections with the area greater than this required. So we need to select a section which have least weight, and least are the smaller size. So smaller size as well as the least weight, minimum weight. And the connected leg width should be greater than minimum. So the width of that section of the connected leg should be more than this B minimum. For example, if we are considering this angle section, so the length of the leg should be more than this B minimum. And the compatibility of connection with other member is to be provided. So we need to keep in mind that we have to connect this member with the other member. So based on the requirement of connection, we need to select the shape. Either we can go for angle, C or W. So that will be decided based on the connection requirements, that it should be compatible with the other members. Okay, so once we have selected the trial section, so then we will perform the capacity checks to see whether our selected section is safe under the application of load. So find actual value of U and AN if rivet pattern and diameter of rivets are known from the connection design. Okay, so next comes the capacity analysis. So we will use LRFD design method to calculate its capacity corresponding to yielding of gross section and fracture in the net section. So in this video I will not cover the ASD method. So the approach is same in case of ASD, only the difference is we apply the factor of safety on strength instead of loads, and the factor of safety are different from the LRFD method. Okay, after calculating its strength, we need to compare it with the applied load. So if it is more than the applied load, then it is okay. Then we need to check the slenderness ratio limit. If the slenderness ratio is L over R minimum is less than 300, then it is okay. And we also need to check for the fatigue strength as well as the design of lacing. But we will not cover these topics in this chapter. We will cover these at the later stages. For example, the design of lacing we will cover in the next chapter, design of compression. Okay, we also need to design for the end tie. So if we have a C section connected like this, so in plane, so they will be like this. So we need to use end tie plates to connect. And the length of the end tie plate should be 2/3 of S. And S might be if we have a welded connection at the ends. For example, we have welded the plate over here at these toes. So in that case, the length will be the distance between the welds, and if we are using bolts, so the distance between these bolt line will be S. So the length of this tie should be 2/3 of S. And the minimum thickness of this end tie plate should be S over 50. So this will be further discussed in case of compression members when we will study about the design of lacing. Okay, so after that we need to design the connection. So this will be covered in the last chapter. And finally we need to check for the block shear. So once we have the connection detail, then we can check for the block shear, and the block shear strength should be more than that of the strength corresponding to tensile yielding and tensile growth. So at the end, if any of the criteria is not fulfilled, then we need to revise our section. Either we need to go for the larger depth or we need to go for the heavier section. So depending upon the situation, we need to revise our section.